Hello everyone, it's my pleasure to present our work. I'm Shu Fenggong. I'm from Northeastern University, China. The title of our work is HBP Hotness Balanced Partition for Prioritized Iterative Graph Computations. To handle massive graphs, distributed graph processing systems divide the graph data into multiple graph partitions. Then they process them on a cluster of works. However, different graph partition schemes may result in different graph processing performance. For example, in Figure 1, each partition has the same number of vertices, and each worker processes the same number of vertices. We assume the workload only depends on the number of vertices. Then the workload of each worker is balanced, and there is only one pair of vertices communicating between different partitions. It means that there is only less communication between works. In Figure 2, though the workload of each worker is balanced, the communication between workers is large, since there are 3 pairs of vertices communicating between works. Similar to Figure 1, there is also one pair of vertices communicating in Figure 3, but the workload of each work is different. The work with a light workload will wait for the work with a heavy workload, which results in waste of computing resource. Based on the 3 partition results, we can see that a good partition can reduce wait time and communication cost between works. In summary, the goal of graph partition is to balance the number of vertices of each work and minimize the number of edge cuts between partitions. These are some related work about graph partition. However, the existing graph partition methods are designed based on synchronous framework, and they assume the workload depends on vertices or edges. The communication cost depends on number of edges cuts or vertex replications. This is an example of synchronous framework. There is a global barrier after each iteration. One iteration is called a superstep. Recently, some work pays attention to asynchronous graph processing systems, since they can accelerate a class of iterative graph algorithms. In asynchronous frameworks, there is no global barriers, and vertices can be processed at any time. Thus, in each superstep, each vertex is only processed once, and each edge only delivers one message in synchronous frameworks. While in asynchronous frameworks, the number of updates on each vertex and the number of messages passed through each edge are not consistent. In some asynchronous iterative graph algorithms, some vertices always receive more and important messages from their neighbors. They always need more iterations to converge to the fixed point. In this figure, we assume the numbers in vertices indicate the minimum number of iterations required for vertex convergence. Finally, the number of vertices does not indicate the workload of our work. We use the vertex balance partition to partition this graph into 2 partitions, G1 and G2. The work 1 and work 2 process G1 and G2 respectively. Vertex balanced graph partition do not take the vertex hotness into account when partitioning graphs. Though the number of vertices is the same in 2 partitions, 2 works are running all the time. There may be a lot of invalid computation in work 2, since vertex in G2 need fewer iterations. Thus, the work 2 is inefficient. For this, we propose hotness balanced partition. In hotness balanced partition, the sum of vertex hotness in each partition is equal. For this, we propose hotness balanced partition. In hotness balanced partition, the sum of vertex hotness in each partition is equal. Because There are more hotness in J2 in hotness balanced partition. There are more valid computation in work2 in hotness balanced partition. Thus, the work2 in hotness balanced partition is more efficient than work2 in vertex balanced partition. In asynchronous frameworks, priority scheduling can accelerate graph computing by selecting hot vertices to process preferentially. The red block in the progress bar indicates the convergence progress of subgraph. A hot vertex can make more contributions to approaching the fixed point. Therefore, though the sum of vertex hotness in each partition is equal, but the work2 is still not as efficient as we expected, because no matter how to schedule, work2 always processes vertices with low hotness. The advantage of priority scheduling in J2 is negligible. In order to make full use of priority scheduling in each work, the hotness distribution of each subgraph should be the same as that of original graph. In summary, the partition goals are as follows. Assign the same amount of vertex hotness to workers. Minimize the variance between hotness distribution of each partition and the original graph. Minimize the communication cost between partitions. The first two goals are for priority the iterative graph communication. No matter in synchronous framework or asynchronous framework, we should minimize the communication cost for reduce communication time or passing messages quickly. We use HGS distance to measure the variance between hotness distribution of each partition and the original graph. A shorter HGS distance means a smaller variance between the hotness distribution of partition and the original graph. Then the second partition goal can become minimize the HGS distance between each partition and the original graph. When balancing the hotness of each bin partition, we find that the amount of vertex hotness of each partition is equal, and the HGS distance between each partition and the original graph is 0. Therefore, the first two partition goals can be combined into one, balance the hotness of each bin partition. We propose the per bin hotness balanced partition, such as shown in this figure. In per bin hotness balanced partition, the hotness of each partition is balanced, and the distribution of hotness values of each partition is the same as that of the original graph. Then the performance of each work is efficient with the priority scheduling. This is an example of per bin hotness balanced partition. The hotness values of vertices are separated into several bins. For vertices in each bin, we partition them into K hotness balanced partition. When partitioning vertices, we also take communication into account. We should maximize the communication between bins in the same partition. Meanwhile, minimize the communication between bins in different partitions. We employ a heuristic method to estimate hotness of vertex. Initially, the vertex with high degrees always has higher execution priority and is likely to be hot, since they always receive more and important messages. Furthermore, width of edge may affect the hotness value of target vertex. Thus, we use the following equation to estimate hotness value of vertex. When a vertex is updated, it always will send. We use the following equation to estimate the hotness value of vertex. When a vertex is updated, it will send messages to its outgoing neighbors. Thus, we use this equation to estimate the communication cost of edge between vertices. In this paper, we propose a stream-based per bin hotness balanced partition. This is an example of stream-based per bin hotness balanced partition. In this example, we omit the edge information. The hotness values are separated into 3 bins. Depth of the grid scale implies hotness. For each scanned vertex, we assign it to the partition with low hotness on the corresponding bin and low communication cost. The current vertex should be assigned to first partition because this vertex belongs to third partition and the first partition's third bin has the smallest hotness. Similar, this vertex should be assigned to third partition, this to second partition, and this to third partition. In stream-based per bin hotness balanced partition, we use this equation to select the partition which the vertex should be assigned. In this equation, the first part describes the imbalance cost, while the second part describes the communication cost. Finally, I demonstrate the experimental results. This is the configuration, competitors, and datasets. The SPB HBP is our proposed stream-based per bin hotness balanced partition. These figures show the runtime of graph algorithms when partitioning graph by our SPB HBP and its competitors. It's shown that our SPB HBP outperforms other partition methods in different datasets and different graph mining algorithms. These figures show the communication cost of graph algorithms when partitioning graph by our HBP, HBP, and its competitors. It is shown that our partition method results in smaller communication cost than other partition methods in different datasets and different graph mining algorithms. These figures show the runtime of graph algorithms when partitioning graph by SPB, HBP, and its competitors when varying the number of partitions. It is shown that our partition method outperforms other methods when varying the number of partitions. These figures show the computation cost of graph algorithms when partitioning graph by SBP, HBP, and its competitors when varying the number of partitions. It's shown that our partition method results in less communication than other methods when varying the number of partitions. Conclusion: we analyzed the existing graph partition methods and found that they are not suitable for a synchronous graph processing system. We propose a new graph partition idea, Hotness balanced partition. Furthermore, we also provide an implementation of Hotness balanced partition, a stream-based per bin Hotness balanced partition. It's all our work. Thank you very much for listening. If you have any questions, please email us.